Okay, so we're recording. Okay, I'll start right into. Okay, the one way between groups ANOVA. And let me turn off the camera to irritate me. But I'm not that photogenic. Okay, one way between groups ANOVA. So as said, we have had now ample opportunity to discuss the situation where we have two levels to an independent variable. Now we have more than two levels. So we have three or more. And the way this is basically depicted here, and this is quite a good example, essentially, how you would A, depict it, and B, how you have to think about it analytically. So we have here the example of a likelihood of a collision or of a collision while merging. So the likelihood is quantified in a way that we're going to do in chapter 17 with the chi-squared. We're going to talk about likelihood and relative risks. But it's basically, it's in a wider sense, look at it as a probability. So you have a probability to actually have a collision while you're merging on a highway. And there's a certain probability attached to each situation. So either you are on a cell phone, which you have the highest risk, or you're on a video phone, you have a lower risk, which to this day doesn't make any sense why a video phone would have less probability than a cell phone, but never mind. Then we have the passenger condition where you basically have a passenger next to you. You have a chatty person next to you that talks a lot, will distract you too. And then you have the drive along condition where you're fully focused on what you're actually doing, except for when you're doing something else. But yeah, so basically, so you have differences between the four different levels of the independent variable that basically affects your probability. So the ANOVA would be one of these examples where you could actually test these four conditions. And you could test with knowing here a variability of this probability, which we haven't discussed the law of, we have discussed the law of large numbers, but we haven't really discussed how to calculate confidence intervals or some form of variability around the probability estimate. But basically, you can also estimate a variability. So you're utilizing this variability to basically use it for hypothesis testing for all these four different conditions. And we will talk about this in more detail, but essentially what you're testing is a comparison between all these four conditions to the mean of all four conditions. So you have a mean estimate of this sample population, of this level, of all individuals in that level, or all that situations or cases within that level. You get a certain variability, and you do have a certain variability around the mean of these four conditions. So you get a mean estimate for each level, and then you get a mean of all the means. And both of these do have independent variabilities. And basically what the ANOVA is doing, it basically calculates the probability of either one of these conditions being different, significantly different from the mean of means. And I know this sounds a little tricky right now, but we'll get to that. So basically ANOVA you're using with one or more nominal independent variable and a scale dependent variable. So why one or more? Keep in mind when it says one or more nominal independent variable, you have a one-way between groups ANOVA. Between groups means these are the groups. One way means it's one variable, driving condition. If you have a second variable, and we will not do this in this class because I think it's beyond the scope of this class. There's an advanced version to that. That's a two-way between groups ANOVA. This is chapter 14 in your books. It's basically a continuation of a one-way between groups ANOVA. The only thing we will do is within groups ANOVA, but we'll get to that next class. Okay, so this is the idea. So we have one or more nominal independent variables and one scale dependent variable, which is the y-axis. Any questions to that? As a concept, this is the prime concept. That's the foundation. So the question is, why do you use an ANOVA? And why do you not just basically do a t-test between one group. So you have A, B, and C. You have 3 groups. You do A and B, you do A and C, and then you do B and C. Comes to the same end, right? The problem is that with each of your hypothesis tests, you basically have a 5% probability of a type 1 error. So each time you're accepting 5% that I'm rejecting something that I shouldn't reject. If I have 3 groups, then I do 3 comparisons, A versus B, A versus C, B versus C. That's 3 comparisons. So the problem is that now the probability of your type 1 error is now inflating exponentially. So you are basically at a 14.3% risk of having a type 1 error. If you have 4 different groups, that type 1 error goes up to 26.5%. If you have 5 groups, you do 10 comparisons, you have 40% risk of a type 1 error. And that goes up to basically, if you are comparing 6 different means, you have 15 comparisons, that's basically you're more likely to have a type 1 error than not. So yes.
Were the dates on the assignments changed?
Dates on the assignments. That's a whole different question. Thank you for.
Sorry, but I
let me look at the syllabus.
Yeah, the opening date and
You
the date are like the due date was meant to be on Sunday, but doesn't open for
It says in the actual homework that it's due in April. It says if you open up the homework when it's due, but on the syllabus, it says the wrong date.
okay? The guiding star is the syllabus. Whatever's on Canvas is then wrong. All right. Okay. Let's go to homework 2. All right. Homework 2 is not available until March 28th and is due on April 11th.
Okay, but I was just double checking with you because the dates on the syllabus, sorry, that the syllabus list, it's not the same. So I just had a heart attack, but it's okay.
Now, let me check on the syllabus. Thank you for bringing this to my attention. It's fun. If Word would decide to finally open, then we could look at this. As said, Canvas can be tricky, so it's easily possible.
I just wanted to be sure I wasn't like saying wrong things.
Yeah, you were asking for a day later on opening, no, on making the due date. So I pushed the due date for a day. Okay.
No, I guess it's right over there, but I'm saying on the syllabus, it just says.
Okay, homework due is opening on 3/29. I'm open it at 3/28, and it's due 2 weeks later.
We have a different date.
Hmm?
We have a different date. It has to be.
Yeah, but.
Yeah, you're not looking at the current version then.
This is what I like pasted in. It was homework 2. Sorry. I don't know if it's. I'll double check.
You have the version of 3/117. Homework 2 is due 3/19. Oh. Okay, that's my bad. No, please don't. Interesting. Yes, so go with the Canvas date. But hypothetically, I could open it earlier if you want to do it earlier. It's fine with me.
Also, April 11th, I don't know, it's also a holiday, so I don't know.
Holiday. Okay.
I'm so sorry. I didn't need to go to class like off track.
That's okay.
I think we come back the 17th.
17, yeah.
So you're not doing holidays? You're not doing assignments during holidays?
I mean, it depends what, I
Uh-huh.
mean, it might be a day that we can't do.
Okay, let me open up the assignment and earlier. We can make this available. How about we do homework opening today? And it's due on April 11. Can we live with that? We're opening it today. And it's due on April 11 as planned. All right. What is today? Today is 3/20. All right.
Are you able to make it due a day after Pesach?
When would that be?
April 14th.
April 14.
No, it's not for Shabbos.
Okay, on the 17th in the evening at 11:59, I want to have it. Okay. All right, sure.
It could be due the same day.
3:20. Yes. There is a quiz probably sometime. Quiz 2 is on 4/17. Yes, correct. Here's your time to study, William. Okay. Can you access the homework?
I'll check right now.
Yes, please. Okay, fabulous.
Thanks so much.
Not a problem. No problem. No problem. All right. So we have now, okay, back to this. Exponentially inflated type 1 error. Therefore, you need a different approach, mitigating and minimizing the risk of having type 1 error, because obviously you don't want to reject something that you shouldn't reject. So the way you look at this, so you basically, yeah, I don't like this analogy with the Swiss Army knife, but basically what you have, you're going from a set distribution where you have one sample and you're comparing it to a population mean. You have the t-distribution where you're using two separate samples and you're trying to compare those two, and then you basically go to the f-distribution where you're basically comparing several distributions amongst each other. There is, let's get to that later. So basically, what will prompt you to think of a set test is that your mu and your sigma is known, and you only have one sample. Whereas with the t-distribution, you either have one sample or you have two samples, which are either two different time points, then it's paired sample t-test, or it's two independent samples, which you're comparing in an independent sample t-test. If you have a sample size of infinity or a very large sample size, usually you get away with sample sizes greater than 30, you get away with a set distribution. If you have 3 or more samples, you're basically using an F. You can use a square of set distribution if there are only 2 samples and a sample size of infinity or a very large sample size. But this is a rather peculiar example. So basically you have 3 or more samples, you will think of an F distribution. And we will talk about the F distribution today. Maybe just briefly, for the so-called F distribution, you have a so-called F-score table. So equally with the set and the T, you're getting now a critical value. So you're basically testing a cutoff value. And if your test statistic is exceeding that cutoff value, which you remember with the set, it was 1.96 for 5% probability on both sides. And with the T, it was the same. It was corresponding to the degrees of freedom. Again, now you have a cutoff value, which is the cutoff value for an F, and you're basically quantifying your rest risk of having type 1 error beyond that point of cutoff value. So we're calculating that F statistic today. And the notable distinction between a set T and F is that the F is basically a unimodal right skewed distribution with only one cutoff value. So as soon as your calculated F exceeds your critical F, you are rejecting your null hypothesis that at least one group is different from your mean of means. And the way this basically is calculated is outlined here on this slide. You're quantifying the variance. You're quantifying the variance between the groups. So that means you have one mean, two means, and three means. And then you have basically a mean of means, and you have the deviation of each individual group from that mean of means. That's the variance between the groups. And then you have a variance within the groups that is quantified based on the variability within that group. So when you look at this graph again, with the likelihood of collision, you basically, your variance between groups is you have one mean that goes somewhere here, and that's the variation between the individual group means from that mean of means. And the individual within groups variance is this variance indicated here, that's within the group. So dividing this variance between the groups over the variance within the groups gets you to an F. Why is that? Because this basically allows you to relate these two variance estimates, and they have to be in a certain relationship, so they're not supposed to differ that much between the groups. So the sample size needs to be somewhat comparable. You speak of that the variance between the variance within groups should not be more than 20% different from the respective groups. So there needs to be some comparability between the group variance estimates. Excuse me. So the variance between groups divided by the variance within groups gets you an F. You're testing then this individual F for your groups, whatever number that is, against your F-score table, knowing the degrees of freedom of the respective groups in total, and the number of groups, which is the degrees of freedom between. So the difference of the sample means divided by the average of the sample variances basically will then allow you to get you an estimate of this F. In principle, you decide you have these two variances. So this is the estimate of the population variance based on the difference amongst the means. Then you have the within groups. That's an estimate of the population variances based on the differences within the groups. So this is basically the explanation of what I told you before. Then we have three different types of ANOVA. We have a one-way. Well, it's not types of ANOVA. It's basically, this is the nomenclature, how you label this. So one-way basically means that the hypothesis test only includes one nominal variable with more than two levels and a scale-dependent variable. If you have a two-way ANOVA, you have two nominal variables with more than two levels. So you're substratifying again. But we are not getting to that. Just know that the nomenclature basically indicates the number of nominal variables that are being used for the independent variables. In case there one is there, in case there's one or more.
Of the population is based on the statistic or actual variables from the group population, and then why do you need these different types of, like, one way between different groups if you're focused on a certain population already? Is this adding on like a bunch of more?
So if you have, step by step. Okay, so you have one scale variable, that is your dependent variable. And you have one independent variable with more than three levels, three or more, that basically indicates the independent variable. This basically is a one-way ANOVA. If you have a second independent variable and you're substratifying this into even more groups, then you get a two-way ANOVA. Good. Between groups means that it's the variability between those groups. So if you have one variable, one independent, and you have a variance between those groups in the mean estimates of all these groups, so you have three groups, you get three means. These vary from the mean of means. That's your between groups variance. Within groups is the variability within that group, because you have then a group mean, and you have the individual score contributes a deviation from that group mean. That's your within groups variance.
And time. Then you could do like energy. Or like,
For example, yes.
okay, so it's like topics. It's
Yep.
not like,
Yep. Okay. So these are the two variances that are important to basically get used to the F. And we will do an example today which illustrates this a little better and a little bit more hands-on. So basically what's important to keep in mind that you have assumptions that need to be met. And these are basically kind of comparable to what we had before. So you have a random selection of samples. So these samples need to be randomly selected, as previous tests have assumed as well. Then you need to have a normally distributed sample. Again, this is also, it's again a parametric test, not a non-parametric test. Just as an FYI, the non-parametric parameter of the ANOVA is the so-called Kruskal-Wallis test, which we're not going to do in this class. But it's basically, it's a non-parametric approach, which does not make these assumptions. The difference between a parametric test and non-parametric test is that parametric tests assume it's normally distributed, whereas a non-parametric test is not making this assumption. So it doesn't make assumption about the distribution. And then you have thirdly, and we know already, homoscedasticity we've learned already with the t-test. You remember how it utilized the formula builder for building a t-test. And we had, for the type, we had either one was a paired t-test, two, homoscedastic was with equal variance, and three was an independent sample t-test with unpaired variance, unequal variance, which is heteroscedastic. So homo means equal, hetero means different. Scedasticity is basically a comparison of the variability. So if the variability or variance of your groups is somewhat the same, somewhat equal, then you would speak of homoscedastic variance estimates for each group. If you have heteroscedasticity, then they're basically varying between the groups. Homoscedasticity is one of the assumptions for an ANOVA. Again, you can test this formally. There are tests how you can do that. I think the Durbin-Watson is a test to test this, but basically, if the variance doesn't differ more than 20% between each other, then you likely safe. Good. The steps how to do that is again the same as we had with all other hypotheses. So we're first identifying the populations, we're identifying the distribution, and we're making our assumptions. Again, the assumptions is normal distribution, random sampling, and homoscedasticity. Then in step 2, you state the null and the research hypothesis, which is basically that all groups are not different from the over mean. You determine the characteristic of the comparison distribution. You determine a critical value from the F-score table. Then you calculate the cutoff. You calculate the test statistic and you make a decision. Same as before. So now we're gonna go into an example. So example 12.1 is basically the example in your Excel spreadsheet. So this is a sociological experiment. I kind of find this interesting to look at. it's obviously it's a real life example. That's what I like about Norden and Heinzen. They actually use real life examples from either sociological or psychological studies. Obviously, there's only a subset of what really has been studied. So basically, they're studying people in 15 societies from around the world. We're only looking at 4 subtypes. So the researchers were interested whether fairness differs between the groups. So we have 4 different groups. First and second group is foraging and farming, which grew their own food. Third and fourth group, which depended on others for food, which is natural resources and industrial. And in the dictator games, the 2 players were given a sum of money equal to approximately the daily minimum wage for that society. So the first player was always the dictator, could either keep all the money or give a portion to it to the other person. The proportion of money given to the second player constituted a measure of fairness. For example, it would be considered fairer to give 40% of the money rather than only 10% of the money. So now we see here in our 4 groups, we see now the fairness score. So let's go back. So first we identify population distribution and assumptions. So step 1, we have 4 populations. Oops. We have our 3 assumptions, which is normal distribution, random sample, which is not true, and homoscedasticity. We're not formally testing this, but we're assuming it. And then we have, lastly, we have an F distribution because we have, so our independent variable would here be society, and society presents with 4 different levels. So we're doing an F distribution. So step 2. So we have now a null hypothesis where either the extraction and where these societies have on average the same fairness behavior. So that means that the mean is the same for all 3 groups. And the research hypothesis that not all exhibit on average the same behavior. So the way you could hypothetically M1 equals M2 equals N3 equals N4. At least one is different. That would be your research hypothesis.
What does that stand for? What does H0 stand for?
HA?
And H, yeah.
HO and HO is the null hypothesis, and HA is the alternative hypothesis or research hypothesis. Good. So in step 3, we need to quantify now our population characteristics. So for that, we need a degree of freedom between, a degree of freedom within. So basically, the degree of freedom between is the number of groups minus 1. Whereas the degrees of freedom within is the sum of all individual degrees of freedom. So we have, so degree of freedom between is now 4 minus 3 and from 4 minus 1. Degree of freedom within is now 4 minus 1 plus 3 minus 1 plus 3 minus 1 plus 3 minus 1. Step 4 is now to determine a critical value. So now we have talked about, so it is calculated as F variance between groups divided by variance within groups. So between groups is the numerator and within groups is the denominator. If you go on the F-score table, you have in the columns organizers the degrees of freedom in the numerator, which is your between groups, and the denominator comes in the rows. So basically we have degrees of freedom in the numerator of 3 and degrees of freedom of, oops, we actually need to calculate this. This is 4 plus 1 is 3, 6, 9. So we have now 9 degrees of freedom of 9. So degrees of freedom 3 in the numerator and degrees of freedom in the denominator of 9. We are looking for a p-value, and this is here organized within your degrees of freedom in the denominator with the respective alpha. And if we go for 5%, we are finding here a critical F of 3.86. And this is our step 4. Step 4, alpha of 5. Critical F of 3.86. So the F-score table here looks a little different, but basically it presents just in the same format as it is in the one that I provided you with. So basically we have a unimodal right-skewed distribution with a critical F, and that critical F is 3.86. Everything beyond that is the alpha. So now next we need to quantify our F. So again, we have between groups variability and a within groups variability. So what does this mean? So I mentioned it before, and this is one of the best graphs depicting that. I really like this graph. I actually even showed it to my graduate students. It really, it illustrates it very nicely. So we have 4 groups. We have foraging, farming, natural resources, and industrial. We do have a mean in each of our groups. And this mean basically is calculated as the deviation within these groups, right? This is our variation. And now we have, in addition to that, we have variation of the individual group mean to the grand mean. It's called grand mean. So this basically allows now to calculate both of these variances. And it's kind of, okay. So the key here is really to kind of depict this data in a way that it's easy to analyze. And we will look at this in much detail. But what's important to keep in mind, we need a way to aggregate this. And this is commonly being done in the form of a so-called ANOVA source table. So the ANOVA source table basically gives you the source. It gives you the sum of squares, which we know is the squared deviations summed up is the sum of squares. Then you have the degrees of freedom, and you have your MS, your standard error of the mean for that respective calculation, and you have then a respective f. So your standard error of the mean here is basically nothing else but your variance, because you're calculating sum of squares divided by degrees of freedom, and that gets you to your variance. That's how simple it is in essence. Okay, let's do this in Excel. Well, let's actually carry this over. We just can copy it there. Let's copy this over there. This is our f. This is, we can make this a little smaller. Yeah, looks better. Okay, so how do we calculate our sum of squares? So first of all, we have now our respective data entries. So we have here, and I want to also kind of give you an opportunity to learn a little bit of Excel, but we've done this already. If you want to change the direction in which these are oriented, you copy it, and you can now copy it here, and there's this little file you see. You see this opening up here where you placed it. And if you open this, you get a pull-down menu, which you can select transpose. So what you do in essence is you bring it in a so-called long format. And we have discussed this already previously. So you have a wide format, and you're bringing this in a long format. So you're transposing it. And so now you know that foraging is these 4 entries. So now you're doing the same with farming. You can also make a right click on the cell you want to put it in, and you select paste special. Same story. You go and say paste special, and you go and transpose. You know now that these 3 entries are farming. Now you're selecting these 3. You again go and paste special. You again transpose it. And you transpose it. That's industrial. So this is how you have brought it from a wide format into long format. It's considerably simpler. But make sure that you know that transposing can be very, very useful. So I think it's good to know this. And then you can start the calculation. So you first want to have a total sum of squares. A total sum of squares is basically the easiest to calculate because it's an individual x. There's a calculation actually. There's a calculation that makes it a little easier. Yeah. So you have 3 sum of squares that you want to calculate. All right, let's actually start over with, so we have now in the source table, you have degrees of freedom between, within, and total. Your degrees of freedom are quantified as between is 3, we know. Within is 9. And the total is the sum of these 2. So that's 12. And that's just always that way. So if you know how an ANOVA source table is constructed, you will be able to interpret all ANOVA source tables that are being shown at you. And this is important because, again, you may not need to know how to do analysis. You may not need to know how to program R or run it in SPSS or whatsoever. But you will certainly be exposed in your further academic career and your further career with interpreting and looking at an ANOVA source table. That's almost unavoidable. So to know this structure and know how to interpret it is quite central, actually. So now we have 3 different sum of squares that we want to calculate. Let's bring this into the Excel spreadsheet to illustrate it. Okay, so we want to know. Ooh, that's not that good. So firstly, we want to make this smaller. Okay, even smaller than this. Okay. So we have here three different formulae. We have between groups is the grand mean from the entire, from all the samples. And we're calculating this for each individual score. So basically it's the individual M of your group minus the grand mean. You have a sum of squares within, which is clear, right? We have the deviation of the individual group from our grand mean. This is exactly this depiction. This is this depiction. So the grand mean is basically this this is the grand mean. These are the group means. So the between groups variability is quantified as the deviations, as the black arrows. So this is the individual mean. Minus the grand mean. So the grand mean is calculated, as you can imagine, as the average of all of these. So that's societies. That's score. That's the M. And that's the deviation squared. Okay. So this is our grand mean. What am I doing? Okay. Okay, so we have our grand mean calculated now. Now we want to calculate first first we need now our M. So our M is now calculated as the mean of the respective society. So this is basically our mean. And now we're locking this in again, just like we did in the past. And we're pulling this all the way up. Gets us 4 times the mean. The most important thing is because you're not allowed to change the degrees of freedom, therefore you need to propagate it for all your individual entries. You're doing now the same for farming. You basically do this for your 3 farming entries. Oops. Again, locking it in. And propagating it all the way down. Now you do this for natural resources. And that basically gives you the average propagated for those natural resources. Now you basically do this lastly for industrial. And this gives you the last 4 entries.
When you copied and pasted the numbers, how did you get it again to paste, like going?
So you basically, you have average. So you build the average of these 4 numbers, and you need to lock this in with the dollar sign.
I'll say when you pasted the scores from
From white format?
Yeah.
You make a right click on the cell where you want it. Then you have paste special. Make a right click on the cell. There's paste special. And that should allow you to select transpose. And transpose will readjust it. Yeah?
Yeah.
Perfect. Okay. So we have now sum of squares between is calculated as m minus gm squared for each individual entry. So that's deviation between squared is now this m minus the grand mean. But the grand mean you need to log in squared. That should be 37.63. So I'm showing the equation. That would be the equation. So if you are in the same formula, so you basically take the individual m minus your grand mean, locking this in that it doesn't shift. And then if you have that formula in here, in that way, shape or form, you just have to click all the way down. It will automatically propagate it all the way down. Important is just that you do P4, or the respective first M entry, minus your grand mean, and that locked in. So that's your between groups variant. All you have to do then to calculate your sum of squares between is to sum it up. Sum of all of these. Oops. Sum of all of these will then be 461.66. So that's your estimate of the sum of squares between. And what you can do then is you go to your ANOVA source table, and you just have to propagate this over there. That's your sum of squares. Okay. So now what's next? Now we have x minus m. That's the sum of squares within. Remember, we are quantifying the deviation within the groups, and we're getting now to sum of squares within the groups. And this basically allows us to get those sum of squares. So now we have deviations within. So the calculation is here. So we have an M, which is column P, and we have an individual score. So the calculation of the individual deviations is basically X, that's the score, minus our M squared. So that basically gets us our square deviations within. And now the only thing we need to do is to calculate the sum of these. That doesn't look right. So that's 1,541. There's something off. Seems to be right. So now sum of squares total. So that's deviation total squared is now x minus gm. So x minus gm squared and logged in. And also propagate all the way down. That does not seem right. So now taking the sum all the way to the right gets us the sum of squares. So that's the sum of squares within. That's the sum of squares total. Okay. Yep. So this is basically the individual score X, which is here in column O for me, minus the grand mean squared. That gives us these deviations squared. The sum of these gives us the sum of squares total. So all you need to do is then essentially direct the sum of squares within to the respective cells. And the rest is simple, right? So now we know the sum of squares. The sum of squares are a little tedious to calculate. I agree with that. And particularly when it comes to the calculation of those locked in cells. So again, you're basically calculating P4, which is the individual mean. So you calculate a mean for each group. You propagate this all the way through for each entry of this group, that they're all filled with the respective means. Then you calculate the difference between that individual score's mean minus the grand mean logged in. That gives you the between groups variance, or sum of squares. And as you can see already, between is substantially larger than the within group sum of squares. Why is that? Because numerically, these means will differ much more from each other than the within group, because within is always going to be less, because there's going to be intra-group variability is always going to be smaller, because if you're testing the hypothesis that there are differences between those groups, you assume that there's inherently something particular for that group, that there will be less variability. So for fairness, your research question is that society different from that society? So if you say this society is fairer than the other one, you would expect these estimates, these individual scores, to be closer to the group mean. So the relationship between those two means and the variabilities are basically determining the probability of these being indeed different between each other. So now you have a sum of squares between, a sum of squares within, a sum of squares total. And what you do with calculating this variance is now the sum of squares, just like we did with the calculation of the standard deviation. It's the sum of squares divided by the degrees of freedom. And that gives you two different variances. And now we know that the F is calculated as degree of variance between divided by variance within. And that gets you to the F. And this F, if you remember the critical F, this F is exceeding. Therefore, in step 6, we are rejecting our null hypothesis. Concluding that that at least one of these societies is different from the grand mean. Okay. Any questions? Yes, please. Excuse me. Homoscedasticity.
Yeah.
Okay, yeah, the homoscedasticity. Sorry. Yeah, it's a little bit of a downbreaker. Yeah, we're not formally testing this. You could test it. Essentially, the way you would do it, you would look at the comparison between the respective groups. So if you would sum this sum of squares up, if you're summing this up, oops,
Bottom numbers, see if they're.
no, you can't. It's supposed to be, so if you have these respective sums divided by 4, no, 3, that gets you an estimate for the within group variance within the groups. So if you do the same thing here, what? Wrong one. R, that's the sum of squares divided by 3, yep. Now you get sum of squares equals sum of divided by 2 is the sum of these 3 divided by 2 is the sum of these 3 divided by 2, 13. So the idea is that it shouldn't be differing more than 20%. So give or take, that's kind of met here, but this is how you would test it. So you look for the within group variance, and you would compare this variance, and you would need to conclude that it doesn't differ more than 20%, which is somewhat given here. It's not really, that one is a bit of an outlier. So hypothetically, it's a good point, actually. So it wouldn't be met, but again, it's a small subsample. It's just, it's not meant to be tested.
But I thought that was like a test.
No, it's not a formal. Well, it would be a formal test if you would do it in a real life, yes. Although it's not really tested. You would need a larger sample size. So this is just a subsample for teaching purposes, right? But yeah, good question, good question. So this is how you would test it. So you you would quantify the variance for each of these groups, and you would make sure they don't differ more than 20%. Okay. All right. So that's our source table. We have a critical F of 8.20. We have a final F of 8.27, which is basically exceeding our critical F 0.27. So we are rejecting the null hypothesis, and we basically know now that at least one of those groups is different from the grand mean. What are you going to do next? So you have these calculations. You have the respective group variances, the 13. This is how you would compare them. You can compare them, okay. Significant difference between means. And now we're getting to the effect size. So the effect size is basically calculated as an R² of sum of squares between and total. So this is now effect size, and this is the R² will come back to us. So this was regression. So with the sum of squares between divided by sum of squares within. No, the other way around. Right? Between divided by total. Sorry. Between divided by total. Basically gives us here an R² of 0.73, which is a large effect size. It is in terms of interpretation, it is the proportion of the variance in the dependent variable that is accounted for by the independent variable. What does that mean? So if you have a total variance that is constituting within groups variance and between groups variance summed up, which the total is essentially, it's nothing else but the sum of between and within groups. You basically,
You go ahead.
yeah, let me finish. Okay, so you're accounting for how much of these differences of that variability is actually coming from the group differences and how much is coming from the within groups variances. So that's basically what you're quantifying. And if you say there's more variance between the groups than it is within the groups, you get a strength of an effect of that level assignment of the independent variable. Yes, please.
R and then F. Because if F also uses those like population groups, I understand this is kind of like I like affecting the overall.
Effect size. So effect size is the group assignment, right? So effect size is sum of squares between divided by sum of squares total, whereas the F is a variance between divided by the variance within. So one is a ratio, that one is a proportion. So it basically puts a weight. So you have an overall variability which constitutes of the variability between the groups and the variability within the groups. And the sum of this is basically your total sum of squares. And then you find out what proportion of that variability is explained for by the sum of squares between. So you put the weight on the group comparison. This one is the proportion of variability that is explained by the differences between the groups. The ratio, the F, is the ratio between the variance between the groups over the variance within the groups.
So
Yeah.
this is more general.
This is the effect size. It's like a hypothesis test where you basically put the weight on the differences between the groups, rather than the actual hypothesis testing and quantifying the p-value. Yeah. All right. Great. Great question. Thank you. Okay, that's the R squared. Of the R squared, there's a addition to that, which is the so-called omega squared. So, so first of all, these are the conventions for our effect sizes. So with 0.73, we have a very large effect size. Omega squared is a deviation or an advanced version of our R squared, which is basically incorporating information of the degree of degrees of freedom. So that it's an adjustment and gives a more realistic estimate of the effects as accounting for the degrees of freedom. But I don't want to spend much time on that. So effects as we have here. So once you have this F, you basically know now that there are some differences between the groups and differences between the groups to the grand mean. What are you going to do with this information? You also want to quantify which group is different from which group. And you can do this with a so-called post hoc test. So pre and post is kind of easy to know what that is. Hoc means event. So you make a comparison after the event of hypothesis testing. So you there are two reasons why you would do post hoc tests. One is that you have found a significant difference. So you found a significant F. That's reason number one. Reason number two is that when you quantified and when you expressed your research question, you had a bland comparison already in the back of your head. And that's essentially what's the second reason.
What did you say the second reason?
It's a bland comparison. An a priori and a posteriori is basically a priori is before you actually did testing. So it's a thought experiment, and you came up with the decision. A posteriori is after you have the results at your hand, and then you make.
After, if there was no significance found with the.
Well, because your research question points in that direction. If you, for example, if you're interested in comparing, if you design a study and you're comparing 4 groups with blood pressures, and you have 3 of them are assigned to this new blood pressure medication at different doses, and you're interested, how do these groups differ? And you do an ANOVA and you find a significant, or you don't find a significant end, or you find a significant, but you knew already right from the start that you're going to do this comparison because you're intellectually interested in these differences, you will still do the differences. But you only do the ANOVA to basically confirm and kind of set the stage.
Start to do a pre/post.
Correct.
It's a hypothesis. It's a hypothesis.
It is. It's during. It is a hypothesis. It's well, essentially, it's depending. It's for each comparison you have one hypothesis. So for each of those hypotheses and null hypothesis, you assume a 5% alpha. That's a priori. That's when you plant this comparison already from the start. When you design your research questions, you designed this already in a way that you wanted to make this comparison.
Or you're already like, this is what it's.
Even if you would do this comparison, even if your F is not significant, even then you would do this comparison. Because with Tachy-Honest significant difference test and Bonferroni post hoc testing, you basically have means where you alter your alpha, and you would find an p-value that is adjusted for multiple testing. That is the beauty of it. Okay, yeah, we're not gonna go, well, no, we need to speak about this next class. Okay, it's 5:55. I think we're done now. Sorry I was a little late, but thanks so much. Have a nice evening.
The team is 4 minutes late because of the appointment that ran a little overtime. I want to know if you can mark me as present. Hold on, one after another. So that's Friday. Your name? Sorry. Oh, Silva Lovic. Yeah. Okay, got it. Thank you. Sorry, I forgot your name. Thank you. Bye-bye.
No.